We covered last time the regenerative cycle for the Brayton, the reheat, and the intercooling. When you put them all together, so you could have a regenerator, you could have, basically this is reheat, or you have a combustor after the first turbine. And then the intercooling was to reduce the amount of work for the compression. So all of those enhance the performance, increase the thermal efficiency of your plant. The question that we left with last time was, what is the minimum work per unit mass? So I have a device, I have fluid flowing in and fluid flowing out. In the first case, it's water, H2O, at a pressure and a temperature. Pressure is 100 kPa and a temperature of 25 degrees C. And I boost the pressure to 1000 kPa. Well, we know that water at this state is subcooled liquid. Okay, so it's liquid water. Hence, this is called a pump. And we feed energy, mechanical energy, to the pump. And so the minimum work per unit mass is going to be calculated by, assuming internally reversible compression, it's going to be approximately V P2 minus P1. So the specific volume 1 over the density, 0.001 meters cubed per kilogram, a number you should remember for water, and then just 900 kilopascal increase in pressure. And so for water, we expect that it'll cost 0.9 kilojoules of work per kilogram of water. It comes in subcooled or compressed liquid. It leaves subcooled or compressed liquid. What is the final exit temperature? T2. We concluded that it's around 25 plus a skosh. It's around 25 degrees C. Right? Take a look at that temperature entropy diagram. Go back to the Rankine cycle. Look how close all those curves were down in this region. And say to yourself, I'm going to have isentropic constant S, compression from some compressed liquid state to another compressed liquid state. It's just at a higher pressure, and it'll be like right above. And so the increase in temperature is small. That was last chapter. That was vapor power cycles. That was with water. Now we have Brayton cycles, gas power cycles, air, ideal gas. So we ask the same exact question. I have a device. I'm going to bring in some fluid. This time it's air. I'm bringing it at the same pressure, 100 kilopascal. I'm bringing it at the same temperature, 25 degrees C. And I suspect that I'm going to need 298 Kelvin, because a lot of times we use things like PV is equal to RT, ideal gas equation. You always need absolute temperatures in there. We will come out at state 2 with a pressure of 1,000 kilopascal. Same pressure increase. We ask ourselves, what does that work? What does that work? It's the integral of VDP. If you assume it's reversible, right? We think in our mind we have the image of the pressure volume diagram going from this low pressure P1 to high pressure P2. Somewhere the process looks like this. It goes like that, right? And it's the area to the left of that curve. If it's reversible, that would be the minimum work. Well, it's a little bit of a challenge to solve for it, but the way you would do it is you say, okay, I'm going to assume it's ideal gas, I'm going to assume it's reversible, and I'm going to recall an equation that says that T2 divided by T1 is equal to P2 divided by P1 to the K minus 1 over K. Have you seen that equation? One of our most popular equations for this chapter dealing with gases undergoing isentropic processes. There's assumptions here. Don't apply this for water. Don't apply it for two-phase steam. You know, It applies for an ideal gas, a constant specific heat undergoing an isentropic process. So we can calculate the temperature at 2 first. We'll actually answer this question first. So the temperature at 2 is 298 times 1,000 divided by 100 to the 1.4 minus 1 divided by 1.4. And when you run that number, you calculate a temperature of 575 Kelvin. If I want to calculate this work, this way is conceptual. I have an illustration, but I can just do an energy balance, and I know that that specific work is equal to H out minus H in. True or false? Add constant specific heats, C sub P, T2 minus T1. True? Constant specific heat value from memory for air, cold. You know, we're getting approximate numbers. I'm not trying to get 3 significant digits on that number. It's close enough to 1. I can call that number 1. I know it's 0.9, but I'm not struggling. Is it 0.921 or anything like that? Same here. I'm trying to get in the ballpark. So what's the specific heat of air? About 1. Okay, 1.005. It's about 1 kilojoule per kilogram Kelvin. Is that somewhere in your memory too? Good. And now you have the two temperatures, 575 minus 298 Kelvin. And guess what the work is? The work is a whopping 277 kilojoules per kilogram. Let's see. Compare 0.9 to 277. It's over 300 times larger. You know, I'm really an investor on the side. I teach mechanical engineering for fun, but I'm an investor. You give me $1, I invest it in my Ponzi scheme, my investment scheme, and I give you $300. Would you do that? I mean, I know if it was legit and you actually got $1 in, 300 out, you would be excited. I'd have a line longer than the iPhone 6. I want to purchase an iPhone 6 line, right? Waiting to take a hold of that. This is a big deal. This is a huge difference. Think about it. What did we change in this problem statement and this problem statement? What did we change? Air to water. Did I change inlet temperature? Did I change inlet pressure? Did I change outlet pressure? But it is such an important thing to get out of this class. It takes a lot of energy to, we don't call it a pump, we call it a compressor, to compress air. And it takes very little energy to pump water. Okay? So hopefully you enjoyed it. Also, the temperature at state 2, the exit temperature is 300 degrees C. Do you want to touch that? You want to let that blow over your skin of your hand? Did I do the math right? Yeah, you're checking me. I see your calculator hand. Thank you very much. I appreciate that. This is hot. So when you compress gases, ideal gases, and we're talking not heat exchange with compress, just adiabatic compression, the temperature as well as the pressure skyrockets. The temperature of the gas goes up. What did the temperature of the water do? Stay the same. Stay the same. Let's continue on. What happens if they give you the isentropic efficiency of the compressor, or the isentropic efficiency of the turbine, or the heat exchanger effectiveness? What was the symbol? Eta regen? Can't remember the symbol this book used. Some effectiveness for that regenerator. Okay? Well, first of all, the effectiveness of the generator means on this temperature entropy diagram that the temperature at X is going to be less than the temperature at 4. Because if it was 100%, Tx would equal T4. It would be a perfect cross-flow heat exchanger. All right. Likewise, Ty would be equal to T2 if it was 100%. But if it's not, Ty is greater than T2. That's the first thing. The second is if you have the isentropic efficiency of the compressor, You first go from state 1 to state C as if it's isentropic. You get the work, and then you get the actual work for the compressor, which you divide by the efficiency, and it's more work is needed. More work means it comes out at a higher temperature. So the temperature at C isentropic versus the temperature C actual. So it's the same pressure. This line right here is a line of constant pressure, right? Between the state CS and state C, but the temperature at C is greater. Put the dashed line indicating increase irreversibilities, increase entropy. S, the entropy at state C, is going to be greater than the entropy at state 1. That all makes sense? We've analyzed compressors before. So you have to analyze that component. And for this problem, you might have to analyze it twice because you have two compressors. So the same thing, from D to 2S and then D to 2. Now, if you come to the turbine, you have a higher temperature. TA is higher than TAS. You get less work out of the turbine because of the irreversibilities. Yet you're still on the same pressure. That's all the same pressure line. Okay? So if this is a problem, that's a long problem, but the illustration I just showed, you would take numbers and solve for this problem, okay? So you have one intercooler, meaning you have two compressors. You have reheat, meaning that you go back, so you have two combustors, you have two turbine stages, and you come in at this temperature and this pressure, that temperature. Inlet to the second compressor is 400 kilopascal and 300 Kelvin, so the intercooler cools it all the way back down to 300 Kelvin. On this illustration right here, this TD and T1 are often the same temperature, meaning the intercooler brings the gas all the way back down to ambient temperature. It doesn't have to. It could have brought it down to some temperature above, but that's often what you have in the problem. And the inlet to the first turbine is 1100 kilopascal and 1450 Kelvin, and the inlet to the second turbine 400, and then it's reheated or more combustion up to 1450 Kelvin. You have isentropic efficiency for the compressor, the isentropic efficiency for the turbine, and the regenerator effectiveness. So this is a long and tedious problem. Can you solve a problem like that? I hope you can step through it, right? What favorite equation would you use? T2 divided by T1 is equal to P2 over P1 to the K minus 1 over K. All right? And that's for isentropic process. So for this application, I'll just do the first compressor. So the temperature at CS, why C? Trying to be consistent with the textbook. That states C after the first compressor, right? CS, so is equal to T1 times the ratio of P2 or PC divided by P1 to the K minus 1 over K. The temperature is 300. Pressure at C is 400 kilopascal, and the pressure was 100 kilopascal. And then you have the 1.4 minus 1 divided by 1.4, and you get a temperature that jumps from 300 to 445.6 Kelvin. So the work that the compressor first stage isentropic specific heat times TCS minus T1. Use the specific heat of about 1.005, and you come in with that work to be 146.4 kilojoules per kilogram. Now, what is the actual work? 1 over isentropic efficiency of the compressor times the isentropic work. That isentropic efficiency was 75%, 0.75, 146.6, and it's 195.2, meaning you have to put in more work because of the irreversibilities to achieve the pressure increase to get it from 100 to 400 kPa. So you can now find the temperature at C. The temperature at C is going to be the temperature at 1 plus the work actual into the compressor divided by the specific heat. Find that the actual temperature at C is 494.1 Kelvin. So instead of coming out at 445, it comes out 494. It's warmer. So as I look back here, you could actually start putting numbers. This number for TCS, 445. This number for TC, 494. They're at the same pressure but higher temperature. That was all for what? Just the first compressor. All right? And then you got to go to the second compressor. Then you got to go to the turbine. So your work is around there. And then what about this heat exchanger? Well, let me just share something here. I can't walk through this cycle and calculate with the temperature at X without knowing what T4 is. But it's like you start a problem knowing T1 and walk this far, and then you know the outlet condition of the compressor. They tell you the outlet temperature. So walk from the outlet of the compressor through the turbines to get to T4, then come back and analyze the regenerator. Okay? We've analyzed turbines, we've analyzed regenerators, and I've explained why they should improve performance. I'll quickly show you an Excel spreadsheet that solves this problem. You know, it becomes so tedious, right, that you just want to give it over to the computer, which is good at doing tedious things. That's what a computer is good at, doing tedious things. So the pressure ratio was total of 11, constant specific heats, R, K, and then I get tired of typing K minus 1 over K, so I just compute it once. And then when I need it, I go call it, right? And then I put in bold, like, oh, these are fixed coming in. So I know there's state C, there's state D, there's state 2, there's state X, there's state 3, there's state A, there's state B, there's state 4. This notation, I'm trying to be consistent with the book, and then state Y. Specific volume column I don't really need at all. I just like to put it in and look at them and see if things are reasonable. But the pressures are straightforward. You don't put those in right away. And then it's bouncing up and down to get those temperatures. Just like I showed you, the equations to apply the temperatures. And this temperature was fixed coming in, so it's like you solve down to, you can't solve for X right away. And then you solve down and you can finally solve for state 4. Knowing the temperature at 4, then I can finally solve for X and Y. Okay? But I do it in kind of a step, like I calculate the isentropic work. I'm given the efficiency of the first compressor stage. I calculate the actual work of the first compressor. And I use that information to then get the temperature here. Okay. I then actually compute all of the Q's for each component and all of the works. Some of them are ridiculous, but here is the Q for the first compressor. Why is it 0? There is no heat transfer in the first compressor. We assume it's adiabatic. And then you have Q in the IC intercooler. The intercooler, what's the heat transfer per unit kilogram of air going through the heat intercooler? It's negative because it's out, 195.2. All that is C sub P, well, it's delta H, but C sub P times the change in temperature, right? So it comes out of the intercooler, what, at temperature D. Temperature D minus temperature C. Temperature at state D is 300. If I sum this column right here, what does that give me? Q net. And if I analyze each component for the work, and I sum all of the works for the entire cycle, notice that I have to put in a rejection heat exchanger. Notice I close right here with a heat exchanger which rejects from Y to 4. I have to have that, otherwise my energy balance won't work for the cycle. But often in the book, they don't show that. But this is a heat rejection here, so that the air analysis, the air keeps going in loop. This work net checks. They're the same. If they're not, find my error. How many people used that scheme when you were doing the project? Did you find that you had to check your own work? And like, wasn't it so helpful? You know, as an engineer, you don't want your boss to find your problems, your errors. You really don't. You would like to find them and fix them before you give them to your boss. You and your boss, your team at work, would like to get your own errors fixed before they go out and maybe a client finds them. Because when an error is made by an engineer in a company and then it leads to loss of profit, etc., or even loss of life, blah, 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 it's tremendous, it's compounded. So as engineers, we like to look for ways to check our own work, have confidence in what we produce. And then the efficiency and the back work ratio are calculated there. Good enough? Let's take a look now at some animations, because I think, and Jeffrey helped me find these. So this is a gas turbine. It's easy to put a little box. Oh, there's the compressor. Oh, there's the combustor. Oh, there. But engineers got to make it work, right? And how do these things look? I don't even know which end is it. What end is where? What is this? I don't know. Let's take a look. Couple things. It's a GE. Okay, so it's a real one. And I know it's an animation of it, but it's pretty good. Okay, that's going to be a constant theme throughout any career in power production. Low NOx, low emissions of sulfur or mercury or other things. It just is here. It's going to only become more and more important. Now this is why I wanted to show it to you. Did you catch that? 11 stages, 17-to-1 pressure ratio. There's so many comments I want to make. See how they have those cans sitting around, maybe about 6 of them? That's where the combustion occurs. And so they're taking the compressed gas and bringing it up on the outside of the can, and then they're actually coming through the middle of the can. And they're trying to hold that flame in the middle and stuff. I'm going to go ahead and stop, but you can see this is all for the air intake. And then it goes through and then it exhausts, and you'll have a shaft. You can connect that modular power somewhere else, okay? Here's another one. So all those stages, that's going to be for the compressor. You can see how the stages squeeze it down to a smaller volume as the air flows. They're going to start now showing you airflow coming in. Through the different stages, boosting its pressure. Unfortunately, the temperature goes up too. You don't want that. You want the pressure increase. You have rotating blades and you have stationary blades, rotor and stator. Then finally, the air is going to come up and go around the outside of the bucket. Okay, the coolant. And then it comes in. And one of the reasons I wanted to show this one especially is when he turns, he'll orient it. You could see what they've done right here. They like swirl in combustion. Swirl, good mixing, air-fuel mix. This is just one concept of the design. And a lot of that mass flow of the air doesn't combust. It would be too hot. So a lot of that airflow is good high pressure. It'll expand. It's getting heated. They're showing you now some fuel. This doesn't look like a Siemens or a GE. I don't know what this is, just illustration. The hot combustion gases pass over a turbine blade right here. It's a compressor turbine. What? Compressor turbine. It's the turbine that drives the compressor. It's connected on the shaft with the compressor. Then after the compressor turbine, you may burn some more fuel. Different designs. See the rotating? That's the compressor turbine illustration. So now we're making it hotter, but it's at a lower pressure already. And it goes over the turbines that actually produce the shaft power to do some useful work. And go back to this. So we showed a little bit about the combustion in the gas turbine. How do they use gas turbines? They use in helicopters. This is, I just grabbed off the internet. What does LAPD stand for? Police helicopters, so flying over cities. This is the Bell 206 helicopter, and so this is a engine that drives it. Now, it looks completely different configuration. Well, they had to package it and put it somewhere that's going to go in the aircraft. But let's go ahead, and this guy does a pretty good job of explaining. Also, where do we see gas turbines used? This is an Abrams tank, and so to see one like this is incredible. And there's a gas turbine that drives it. Doesn't look like much, doesn't it? It's a completely different configuration, but the same principles, right? The engineers had to put it together and make it work for this configuration. This is the A12. I don't really care about the most recent version. It's the Abrams tank, but they have the same power. There's more to watch, but it's not turbine related, okay? What I did was I wanted to show you, this is an illustration of that tank with that Honeywell's AGT 1500 engine. And they bust it out, and there it is. There's that power plant. See it? That's the gas turbine. And then it slaps back together for the tank, so you can kind of see how it is. This is an article published in 1982. The tank's been out for a while, okay? So if it was production in 82, what time frame do you think the engineers started working on this? 60s. In the 60s, okay? So there's been more updates and a lot of work to it. But even in this article published in 82, you could see the low pressure compressor, then the high pressure compressor turbine, low pressure compressor turbine, so two stages to drive the compressor, the combustor, then you have some power turbine to actually get the and then the shaft, the coupling for the power production. There's some gearing inside, and a recuperator, which is basically a heat exchanger. There's just another illustration of it sitting in the package in the tank, and a cutaway looking at this. Well, also ships. We should know where gas turbines are in ships, and military vehicles, military vessels is very powerful. You can move, and so this is a LM 2500 gas turbine made by GE. I didn't want to pump out too many videos, but guess what? There's another ship. This is an old article. This is 2001. And it was nice in 2001. They're saying we've got over 10,000 hours of gas turbine engines running on these cruise ships. Also, a lot I mentioned about electricity production. So if you're producing electricity, you're probably building right now gas power plants. And so this was an interesting article. Look when it came out, 10/1, and it talked about General Electric and signed a contract to put the gas engine technology with a 30-year contract service agreement for a 50 megawatt unit in Colorado County, Texas. Anybody been there? It's not too far from Houston. Well, if you're going to make electricity, you want to get as much out of that fuel, that expensive fuel, as you can. You want to convert as much of that energy into electricity and sell it. So today they're going to have a gas turbine power plant, but it's going to be a combined cycle power plant. They won't have this on the helicopter. They probably don't have this on the ship. Okay? They don't have it in a tank, but they have it in a stationary electric generating power plant. So they'll have the gas Brayton cycle and then the vapor Rankine cycle. It just makes sense. So you take the expensive fuel in the combustor, and now you have some spanking hot exhaust gases. You can put that through a heat exchanger. It'd be a heat recovery steam generator, steam generation unit, and then something out the flue, okay, the exhaust at low temperature and clean. And from this heat exchanger, you have generated a lot of steam, and that goes into the vapor power cycle, which we've studied. And so this type of power plant is making a lot of headway. Highly efficient, environmentally friendly. It's the air going through the turbine, burning combustors. Now this, I just have to orient you. This is the heat recovery steam generation unit. So the exhaust gases are coming off of that. And now we'll just continue. That is now water. They're showing steam. Okay? It's being piped out and brought back to a steam turbine. That'd be a high pressure steam turbine. Then go back for reheat. Pipe it back, low pressure and intermediate pressure steam turbine. Finally take the steam to a condenser and a pump and bring it back. So it's now ready to go. I think I have encouraged you to learn a little bit about the electricity that you purchase and what is the primary fuel source for its generation. The city of San Antonio purchased the local utility in 1942 and named it City Public Service. And it's the largest municipally owned electric and gas utility company in the nation. So very, very unique. It's the largest, selling to more customers, more energy, electricity, and natural gas than anywhere in the state of California, New York, anywhere. It has a very diverse energy source mix with quite a bit of nuclear, but the percent natural gas is going up, and the percent renewables is very high. The footprint, I think I showed this to you, is essentially Bexar County, a little bit of not Bexar County, but the rest is, and then some of the surrounding counties, Comal, Guadalupe, etc. What is this right here, bordering Guadalupe? What is that? Cibolo Creek, right? Some areas it's wet, some areas it's dry. True. This is just a straight line, they had to cut it somewhere. In 2012, they purchased the Seguin power plant, Rio Nogales. All right, and it's the name of a street in Seguin that's the power plant's named after. 800 megawatts combined cycle natural gas plant. You could see it has 1, 2, 3 systems, so it's very modular. This is right in this area is the air intake for the gas turbine, and then the heat recovery steam generation unit. And then what it looks like is they all pipe out and come back to a separate building for the steam turbines. So it's decoupled. And then the footprint, it's like, where's the heat rejection? Right here it starts and it goes right over here for those mechanical draft cooling towers. So I took a look at aerial, looking down at it. That last image was this direction. It just caught the corner of that building. And so these are the mechanical draft cooling towers. You have to reject it to somewhere. 3 flues, heat recovery units. You have the gas turbines, gas turbine with electric generator, and the intake to them. Then you have a lot of piping running from each of these systems over to a system. I think it's in here. I don't know exactly. Maybe this is controls and operations building for the the steam turbines and the steam electric generator. And what's all this? Electric substation, and put it out, bump the voltage, and sell it. Okay? Maybe you see that, not really over here. All right. I've never toured the plant, but you can definitely see it as you're driving just past the Guadalupe River. It's right there.